Hi Pre-Calc, we're going to talk about polar coordinates. But before we can talk about the polar coordinate system, we have to make sure we know what we're oh my gosh, that was supposed to be a straight line. We have to talk about what our XY axis business is all about. So this is 1, 2, 3, we'll say 1, 2, 3, 4. All right, so we've got the point 3, 4, and this point is a part of our rectangular coordinate system. Sometimes it's called Cartesian. So if you ever see that word, that's what we're referring to. And this is what you guys have been using pretty much your whole education life, right? Like x comma y. But this is not the only way we can talk about a point. We can consider this point based off of two things. Based off of the angle right here and the distance between, let's say, this point right here and the point itself. So let me draw that over on this side as well. Here is the point we are interested in. I'm going to label this O, this guy up here P. This axis on the horizontal is going to be known as our polar, oh my gosh, I'm sorry, polar axis. And the angle here, we're going to say is theta, and this length is r. This point right here is known as r comma theta. So let me just recap everything we just wrote down because it's kind of important. The distance from our point in this picture O to P is known as r. You can think of it as radius. And the directed angle from the polar axis to the terminal side, which in this case is the segment OP, is known as theta, this angle measured here. So these coordinates are on something known as the polar coordinate system, which does have kind of that cross-axis thing that we know and love, but instead of having the rectangular coordinates, we actually have a bunch of circles. So it looks like a target, basically. And we move with relation to how many radii out we are and the angle that we are at. So maybe this right here is the angle pi over 6, and that would be 3, because I'm 3 radiuses out. So that's the point 3 comma pi over 6. So we're going to take a moment and practice plotting some points together, because this is a big piece here, and I'm going to, if you would like to pause the video to write these down, that would probably be helpful, but I'm just going to jump right in. So my first point is the point 2 pi over 4. Sometimes I think it makes more sense to start by identifying where your angle is. So here's pi over 4, and then I'm going 2 on my radius, and so here is the point A. For B, let's say, okay, 11 pi over 6, so that's not quite 12 pi over 6, which would be 2 pi. It's a little bit less than one full circle. It's probably somewhere over here, and I am going 1, 2, 3, 4 out, so this is point B. And you don't necessarily need these lines. This is just kind of to help us. So let's try one without the line. 0 pi. All right, well, pi I know is the negative x-axis, and I'm not moving out at all, so 0 pi is kind of like our origin. And then last but not least, what about the point 3 negative pi over 3? Well, we know what a negative angle looks like. It opens down, so negative pi over 3 is going to be down here, and then we go out 1, 2, 3. So that is D. And then last but not least, we have E, which is 5 pi over 4, or 2, 5 pi over 4. Well, 5 pi over 4 would be 1, 2, 3, 4 pi over 4. Here's 5 pi over 4, and then out 2. So this is E. But notice, in each of these, The radius is positive, greater than 0. Well, what if we are given a point where our radius is not positive? Because that's an option here. And let's look at this. So what if our radius is less than or equal to 0? What if our radius is negative? Let's consider the point 2 pi over 6 for a second. 1, 2, I'll make 3 here. Sorry, those aren't perfect. All right, here's pi over 6, and here's 2 pi over 6. That's the point right here. Notice we started at this positive x-axis, and we opened up a distance of pi over 6. Now, if our radius is negative, so let's change this. Now let's look at the point negative 2 pi over 6. To do this, we are going to start our angle from the negative x-axis, and then we'll keep moving in that same counterclockwise direction. So here I'm going to start from the negative x-axis, and I'm going to open a distance of pi over 6. This is still the same distance, angle measure, it's just starting in a different location. And then we go out to that radius of 2. Notice, what's the same about these? Well, they are the exact same line, right? If I were to draw a line through both of those, it would hit it exactly. So one note we could make is that this point will be on the terminal side of whatever that angle is plus pi. So this point right here, well, here's pi over 6. If I add a distance of pi, half of a circle, that's where I'm ending up. We're going to practice these in class together. So if you want to pause the video and write these down, that would be a good thing. This will be like one of our warm-ups. But the other thing that we should talk about is that we can find, there's going to be more than one polar coordinate for any point. So if we've got our good old polar coordinates, think about it. Well, here's a point, let's go with 3 pi over 4. But is that the only way we could name this? No, because pi over 4 would be if we open up. I could also open down. I could go all the way around. So it would be 3, what would that be? Negative 7 pi over 4. Or we just talked about the negative radius. What would it look like to have a negative radius? So let's think about this. Let point P have the polar coordinates r comma theta. Then any other polar coordinate of P must be of the form. Well, let's start with this first idea. We could make it r, same r, and then we could take that angle measure and add or subtract 2 pi n, where n is any integer. That would be like the example I drew right here, right? We add one circle, or we subtract one circle, or we add 3 circles. We'll still be at the same angle because we have coterminal angles. This is not the only way though. Or what would it be if we made our r negative? So now let's consider, how do I get to this same place, but starting from here? Well, that would be 4 pi over 4. That would be 5 pi over 4. This would be negative 3, 5 pi over 4. All 3 of these polar coordinates right here are the exact same point. They're this point right here. So how can I write this in a general form? Well, if we change r, we are really adding, remember how we said it's the exact same line? How much are we adding? Well, we are taking that angle and we are adding or subtracting pi times m, where m is an odd integer. Notice we don't want to add a full circle. We only want to add half of a circle, a distance of pi, or we could add 3 pi or 5 pi or 7 pi, any sort of odd version. So again, I'm going to let you pause the video if you would like. We're going to do this example together. Find 3 additional polar representations of the point 3, 5 pi over 4. Uh-oh, that's kind of similar to the one I did, but that's okay. And you're going to be asked to find a negative theta, a negative r, and then whichever you want. But this will be something we do in class. The last thing in this video is going to be talking about changing between the polar coordinate system and the rectangular coordinate system. And of course we can do that. So let's draw these both on the same axis. If this is the point r theta, that means this distance right here is r, and this angle right here is theta, but we could also name this point xy, where this is our x distance and this is our y distance. Well, what do we have here? We have a right triangle. We have a right triangle with 3 sides and an angle measure. So let's look at our trig ratios. Sine of angle theta is equal to opposite over hypotenuse is equal to y over r. Cosine of our angle theta is equal to, so c adjacent over hypotenuse, x over r. We could look at tangent of that angle, opposite over adjacent, y over x. Or we could look at the fact that this is a right triangle, so x squared plus y squared is equal to r squared. And so I'm going to just put these all, the exact same statements, in one last little nice box down here. So let the point P have the polar coordinates r theta and rectangular coordinates x, y. Then, well, the first statement, x squared plus y squared is equal to r squared, is true. Notice if I move r to the other side here, we get that x is equal to r times cosine of theta. Well, that seems kind of familiar. It's very similar to our vector thing, that the x-coordinate of a vector is equal to the radius or the magnitude of the vector times cosine of theta. And we could do the same with our sine. Y is equal to r times sine of theta. And then tangent, we're not going to rearrange. Tangent is equal to y over x. This is the most important piece in this section. I am now going to show you the last examples, and if you'd like to pause the video and write them down, that would be a good idea. Find the rectangular coordinates of the point 2, 7 pi over 6, and find the polar coordinates for the point -1, 1. If you want to pause the video, please do so to write those down. Otherwise, we will be converting r is equal to -2 cosecant of theta to the rectangular form, and we're going to identify the graph. So pause the video if you'd like. And our last one is to describe the graph of the polar equation and find the corresponding rectangular equation as well. R is equal to 4 cosine of theta minus 4 sine of theta. Have a wonderful rest of your day.